If you really want to, yeah. All right, number 5. Synthesis and decomposition. Just remember the other ones. Single replacement.
Double replacement.
Yes. Remember the last one?
It's like a word that doesn't have
Combustion.
It is combustion.
Yeah, combustion has to do with CO2.
Yes. Yes. Becomes water and CO2. Combustion. Okay. So our first equation, let's do the example. The HF plus N2 yields HF3N4. Okay, someone last hour was really stuck on this HF, and it threw them off that this is one element. It's not hydrogen and fluorine. Okay, this is its own element. It's a little f, so they stick together. So I have one HF over here, and I have 3 HFs over here. So I'm going to put 3 over here. And remember, when you're balancing, you're just writing those big numbers out in front. And then I have 4 ends over here, and I have 2 ends over here. So what number in prop makes that 4? 2, because I multiplied 2 times 2 to get 4.
2.
Good job, Jack. What type of reaction is this?
Synthesis.
2 things combined to make one thing. This is synthesis. Synthesis. Alright, next problem. I have 1 magnesium, H2SO4, magnesium sulfate, and hydrogen gas. You guys actually did this in the lab. You did it with HCl, a different acid, though. Okay, let's start with magnesiums. You have a magnesium, and you have magnesium. So those ones look pretty good. We got 2 H's. We got 2 H's.
Double replacement.
Looks pretty good. We got a sulfate and a sulfate, or 1S, 1S, 4 O's, 4 O's. Okay. And so that one's balanced. We're good. And Zach, what kind of replacement did you say it was?
Double.
Try again.
Single.
Single. We got these little singletons out here, and then you have a little singleton over here. So they're only replacing 1 time. So this guy is single replacement. I'm going to abbreviate with that with an SR. Single replacement.
I don't like that combustion.
And then we have a hydrocarbon, C2H6, plus oxygen, that yields CO2 and H2O. These ones are typically your hardest ones to balance, the most complex. So let's start with our carbon. I have 2 carbons here. I have 1 carbon here. So put a 2 in front of it. Okay. Now let's do hydrogens next, just because I have oxygen in 2 places. So I have 6 hydrogens over here. How many over here? 2. So what do I multiply that by to make 6? So multiply it by 3. So now I have 6. How many oxygens here? 2. And how many do I have in this one? 4. How many do I have in this one? 3. Okay. That gives you 7, and we can't get 7 like this. So one way you can do this is just multiply all your current coefficients by 2. So let's change this to 2. Let's leave this blank because we're still trying to find that. Let's change this 2 to 4, and let's change this 3 to 6. And then let's try those oxygens again. 4 times 2 is 8. 6 times 2 is 12. So that gives me 20. So I could put a 10 here, right? I feel like I just messed that up. Oh, this is 6. I did mess that up. This is 6. What's 8 plus 6?
Isn't that 12?
6 plus 6 is 12.
Wait. I thought we were doing 6 times 2 is 12.
We're doing oxygens.
Oh, wait, never mind.
Yeah, that's what I messed it up the first time I did the H's. I need to do the O's. So 4 times 2 is 8, and 6 of those, 6. So then I have a total of 14. So if I wanted to divide that by 2, that's a 7.
So I thought you had to times everything by 2.
I did that already.
So why wasn't there 2 in front of that?
Because that's what I was solving for.
Oh, okay.
I mean, you could have put a 2 there, but then you would have to change it to a 7. So. Okay, so the last thing that you want to do is check all your numbers, 2, 7, 4, 6, and see if you have a common denominator. Because sometimes when you're manipulating an equation, you might end up with something like, let's see, a kid earlier had 6 21, 12, and 18 as their numbers out in front. But you can see you can divide all these numbers by 3 and then get this reduced equation. Okay, but this would be wrong. So sometimes when you're manipulating, you need to look and see if you have a common denominator that you can divide them all by. Because sometimes you just start like multiplying and adding and then you get really big numbers. And then usually when you see those really large numbers, you have a common denominator that you can divide by. All right, next one. PB NO3 2. PB NO3 2. Okay, what do these parentheses mean? Like, how many oxygens do I have here? 6, because I multiply this 2 by that 3. How many N's do I have here? 2, because that 2 distributes to the N's as well. How many PBs do I have?
1.
Just 1, because none of this is for the PB. That's all for the NO. Okay. KI. PBI. Lead iodide. And KNO3, potassium nitrate. How many PBs?
1.
How many PBs?
1.
How many N's? 2. How many N's?
1.
Just 1. So let's put a 2 out in front of that. How many O's?
6.
6. How many O's?
6.
6. 2 times 3 is 6. How many K's?
1.
Just 1. How many K's? 2. So let's put a 2 out in front of that K. How many I's?
1.
That 2 multiplies, so we have 2. And then 2 I's there. So that looks like we're balanced. What type of reaction is this?
Double replacement.
This is double replacement because that NO3 and the I are switching partners. So the PB goes with the I and the K goes with the NO3. So this is double replacement. I forgot to ask this one. What type of reaction is this guy?
Combustion.
Combustion. Thanks, Zach. Anytime you end up with a carbon dioxide and water, then you know it's combustion. Okay, some sort of hydrocarbon with oxygen making a carbon dioxide and water, that is the formula for combustion. Okay, last one. Iron 3O4 yields iron and oxygen. How many irons? 3. So let's put 3 over here. How many oxygens? 4. So we put here
2.
2. Because that 2 times 2 is 4. And now we're balanced. What type of reaction is this guy?
Decomposition.
Yes, because one thing breaking down into more things, it's decomposing. Decomposition. I think I spelled that right. Questions on that one?